Welcome to Ask and Learn.
We have an insulated cylinder which is initially filled with air at a specified state. A paddle wheel in the cylinder stirs the air at constant pressure, and we wish to calculate the final temperature of the air. We assume that air is an ideal gas, the cylinder is stationary and has no kinetic and potential energy changes, there are no work interactions other than the boundary work, the cylinder is well insulated and hence heat transfer is negligible, the thermal energy stored in the cylinder itself and the paddle wheel is negligible, and the compression or expansion process is quasi-equilibrium. Now, the properties of air are its gas constant R, which is 0.287 kilopascal meter cubed per kg Kelvin, and its specific heat at constant pressure, Cp, is 1.005 kilojoule per kg Kelvin at room temperature. The specific enthalpy of air at the initial temperature, H1, is equal to the enthalpy, going back to our tables, at 298 Kelvin is equal to 298.18 kilojoule per kg. Now, since this is a closed system, no mass enters or leaves, we can write the energy balance equation for the system, E in minus E out, the energy in minus the energy out, is equal to the change in energy of the system, delta E. Now, the energy into the system is due to the paddle wheel. So the work done by the paddle wheel is into the system, and the boundary work, WB, is defined as out of the system. Now, this is equal to the change in internal energy of the system, delta U. Now, if we rewrite this and take the boundary work across, we get that the work done by the paddle wheel into the system is equal to delta U plus WB, the boundary work. But we can write delta U plus the boundary work as M into the change of specific enthalpy, which is why we found the enthalpy of the initial state above. So now we have our energy balance equation. And delta U plus the boundary work is equal to the change in enthalpy, and this is during a constant pressure quasi-equilibrium process. Now we have this equation. We first need to find the mass of air that's involved in this process. So the mass of air, M, is equal to P1 times V over R T1. And the initial pressure is 400 kilopascals. The volume is 0.1 cubic meters. This is divided by R, which is 0.287 kilopascal meter cube per kg Kelvin times the initial temperature, which is 298 Kelvin. Hence, we get the mass of air to be 0.468 kg. Now, if we substitute this into the energy balance equation, we can find the enthalpy change. So substituting this back into the energy balance equation, we get that 15 kilojoules is equal to 0.468. 15 kilojoules is the work done by the paddle wheel. The mass is 0.468 kg into the change in enthalpy, which was H2 minus H1, which we showed from our tables was 298.18 kilojoule per kg. So we can rearrange this equation and solve for the enthalpy of the final state, H2, and we get H2 is equal to 330.23 kilojoules per kg. And now that we have the enthalpy of the state, we can go to our tables again and find the final temperature of the system, T2. And T2 from our table is 329.9 Kelvin.